Hello, in this lecture we'll cover chapter 14 in our textbook, the chapter on regression. If you remember, in chapter 13, we talked a lot about associations and we talked about statistical significance. Earlier chapters, we talked about variables and finding the level of measurement for that specific variable. So within this chapter, this is where we kind of bring all these things together. Previously, we talked about tests that tell you association or show you association, and we talked about tests that show you statistical significance. Well, regression is that magical method that shows you both, that combines them together. So we're going to talk about the different forms of regression analysis that can be used, including bivariate regression, multivariate regression, and some regression models that are not exactly linear. We're going to briefly discuss maximum likelihood estimates towards the end of this lecture. But in this lecture, I want to focus less upon how to calculate these things, less upon the math of them, but more so on understanding the concepts and the theory behind them so that you know if you see them in a paper what they are attempting to convey with the different models that you see there. You'll understand the magic that exists behind those different models. So what is linear regression? Well, first of all, linear regression is a broad umbrella term that describes a method that measures the association between two or more variables at the same time and determines whether or not there's a statistically significant relationship between those two variables. It's important to note that linear regression is exactly what it sounds like. It is regression or a method that tries to make a line. Earlier in chapter 13, we talked a lot about lines and we talked about the strength of a relationship. And when two different variables have a very strong relationship, they come together and they have a perfect correlation and you see a perfect line. Sometimes this line is pointed upward, sometimes the line is pointed downward, and upward indicates a positive relationship and downward indicates a negative relationship. But we're going to focus on the method that tells us how to get that line and also the significance of that relationship, because a line indicates the relationship that exists between two or more variables. So as I said a few minutes ago, linear regression focuses on demonstrating association between two or more variables and the significance between them. But going a step beyond that, it also looks at making predictions beyond your sample. So we talked about how you have samples that you have to pull from the population, and then you have to make inferences up to the population about what that relationship looks like for those variables. Well, linear regression allows you to do so. What linear regression does is take your sample numbers for both of your variables, and then it estimates the relationship between those variables, how it would look not just for your sample, but how it would also look in the larger population. So let's say you have points for education and income, and you go through and you have your points for education and income, and you have education years for like somebody who has a high school diploma, somebody who has a college degree, somebody who has a master's degree, and then you have their income levels. Well, what if you want to know the income level or be able to predict what the income would be for somebody who doesn't necessarily have a 4-year college degree, but they also have more than a high school diploma? But that's not a point that you had available within your sample. But what linear regression would do would be able to make that prediction based upon what it had, the data that it generated for the numbers that you did have available, and then you'll be able to make predictions or forecast the income for an individual who falls in that in-between category. And that's the beauty of linear regression. It estimates, it shows association, and it demonstrates significance all with one method. Before, we had to talk about multiple methods to do lots of different pieces of those things. But linear regression is something that's typically saved for our variables that are considered to be scale. So scale variables, again, are those that are ratio and interval variables. They develop this line with the linear regression by generating estimates. So you can do this by hand to calculate a linear regression model, or it's something that you can do using computer software. And it comes up with these things called regression coefficients. And a regression coefficient is basically the estimate of an unobserved population parameter. Parameter is a fancy way of saying what something would look like in the population. So it will generate a number that is suggesting is the inference up to the population going beyond your sample. These are the numbers that we expect in the population based upon your sample. That's what coefficients are. So looking at linear regression, it's not really something crazy that you've never been exposed to or you've never seen before, because it goes back to 8th grade math or middle school math in general, doing slope and algebra. That is all this is. In linear regression, you still work with x's and y's, and as you know, the x's are the independent variables and the y is the dependent variable. Is the dependent variable. And what you could typically do if you had a set of x and y variables, variable points that are scale variables, you can go and you can create a scatter plot. And with that scatter plot, you can plot the points for the independent variable and you can plot the points for the dependent variable. But what linear regression does is plot those points together instead of just plotting them separately. So for every independent variable value on the x-axis, it plots the dependent variable value on the y-axis. So if you have somebody's education, you would take their education and income and you would find that point for both of those on the horizontal and vertical axis where they would meet at that point, and you would put a point there. So it uses that basic equation that you're used to seeing when you were in middle school with math, y equals mx plus b, and that generates like the slope of a line, right? That's what we use that for. What all linear regression does is generate a line, and it talks about the slope as well, and where that slope rests, that is how we determine our predictions for values that we don't have. So we have the y equals mx plus b, which you're used to, but within linear regression, it will be y equals a plus bx. And a is the constant, and you guys are familiar with the constant. That's the thing that is considered to be the value when the dependent variable is not present. It's the value that does not change. It always stays the same. And b would be the slope of the line. So going back to that middle school math, the slope of the line for the points that you provide. And then the x, of course, would be the value that you put in for that x variable, that independent variable there. But I'll show you a little bit about what that looks like. So if you remember, I said that you can plot points. So let's think about our example with education and income, plotting points. So you have a simple scatter plot on the left-hand side where the points are plotted for. Imagine this is for education and income. And you plot the points there. You go across on the bottom part and you plot the value for education, and on the vertical one you're going to plot the value for income, and together you're going to find where those two meet, and that will be your point. And you do that for each of the observations or individuals that you have, and you plot them, and you get all these beautiful points. But it just gives you a bunch of points. You can guess what the relationship is between the two. I mean, it looks like it could be a positive relationship between the two, but you don't have that line there to tell you what the slope is. You don't have that line there to show you a clear depiction of the direction of the relationship and the strength of the relationship. But what linear regression does, which is on the right hand side of the screen, is that it goes and it makes a line through your points based upon the data that you have available. It goes through and determines what would be the best line to fit these points. What's the best way to demonstrate the relationship for those points that you have in your data set? And that is what linear regression does. It tries to make a line in some direction, positive, negative, up, right, left, down, up, down, left, right, based upon your points. And that is what it gives you as your estimate for the relationship between your points. Now, all of this can be done on a computer, but it can also be done by hand. Your book does a really good job of describing the ways to calculate these different components so that you can get all of this information by hand. But I'm not focused on you knowing that, because this is a little bit beyond the scope of this class. But I want to make sure I give you guys a good overview of what all of this stuff is. So how does regression work? Well, it works because it operates under certain mathematical and statistical assumptions that have to be met in order for the math behind all of this to work. And there are 10 classical assumptions of linear regression, and these are the rules, the boundaries that the information you use for linear regression has to fall in order for you to be able to use this method. And a short way of saying all of the stuff that's listed on the right hand side of the screen, because again, it's not something we need to go in depth about, is to say that linear regression focuses on estimating using the blue method, which is it focuses on making the calculations using the best linear unbiased estimates. That's how it comes up with a line based upon the data that you have, based upon your scatter plot and all of that good stuff. That is how it works. And built within the software is all of these different assumptions. And all if those assumptions are violated, the linear regression will not work for the things that you're studying. But that's all I want to say about that because that goes beyond this class. And linear regression works to minimize the sum of squared errors. So as I said a minute ago, it wants to generate a line, right? And it wants to develop a line through your points. Well, it does that by finding where the line should be placed between your points to have the least amount of error as far as their estimates for what each point's relationship should look like. So you remember a minute ago I talked about you want to know the value of somebody who doesn't have a 4-year degree, but they have more than a high school diploma, and that wasn't something available in your data set. Let's say that you do get a data set and it does include all this information for those people. What linear regression does is try to plot the line that is most likely to be accurate or close to what that relationship actually looked like for those people without that information. So it goes into it goes in and it decides that this is the best estimate that will be the least likely to be wrong in order to demonstrate the relationship based on the points that we already have available. Linear regression focuses on establishing causal relationships. Big words we've talked about throughout the semester. We talked about being able to jump over those 4 causal hurdles, and that is something that linear regression really focuses on. And it also focuses on being able to explain variation, being able to explain why the value is higher for this participant and why the value is lower for this participant. So linear regression typically starts out in its simplest form as bivariate regression. So bivariate regression is just like bivariate analysis that we talked about earlier, and that means having 2 variables. And it uses those 2 variables and it comes up with that regression equation that I showed you earlier, which is the y equals a plus bx. But in the regression equation, they actually calculate the numbers for a and for b so that you're able to understand for your specific study, what does that regression line look like? So within the regression model, there are a number of different tests that are also included that we've talked about earlier, one of them being Pearson's R. Now, Pearson's R shows us the correlation coefficient for our 2 variables when we're doing bivariate regression. Remember, I talked about it earlier, by the correlation coefficient can be anywhere between -1 and +1. So one of the things that it generates in addition to this line and that equation that I talked about is a Pearson R value, anywhere from -1 to +1. And I told you whenever it's 1, that means that there's a perfect relationship. And if it's 1, that also means that it's going to be a perfect line. It can be a perfect negative line where it points down, or it can be a perfect positive line where it points up. But that R value here indicates that it is a perfect relationship, that those 2 variables move together in time perfectly together, whether it's in the same direction or in opposite directions. Okay, so the Pearson's R is one of those things that's included with regression, and it shows that level of association. So that's how we get the level of association box checked with regression. The next thing that regression generates is something called R squared, and that is not to be confused with Pearson's R. Pearson's R shows the strength of a relationship between two variables. R squared shows us the percentage of variation in Y. And that's a fancy way of saying it shows us how well our X value explains what we see in our Y value. It shows us whether or not what we did is a good model or a bad model. Are these things like doing a good job of connecting with each other? Or are they like completely unrelated? So the higher your squared value is, because it's on a scale of 0 to 1, that means that it does more explaining and it's a better predictor of Y. So with education and income, if education is a really good predictor of income, then it's going to have a higher R squared value closer to 1. But if education is not a good predictor of income, or let's say another variable like car color, and that would probably not be a good predictor of income, then that R squared value would be lower. So these are all the different little components that regression includes and generates for you in the process to tell you about like your data and what all is explaining there. But remember, Pearson's R tells us about the strength of the relationship. R squared tells us how well our X value explains what we see in our Y value. But now we have to think about it. What if we're in a situation to where we can't do bivariate regression because we don't have just two variables? What if when we're talking about education and income, it's more than just education and income? Maybe a good explainer of income is not just education. Maybe it has something to do with personal motivation. Maybe it has to do with family background, all of these different things. Can we still use regression then? Yes, the answer is absolutely yes. You can still use regression then, but you would not use bivariate regression. You would use a different form of linear regression called multivariate regression. So what is different about multivariate regression compared to our simple bivariate regression? Well, the difference is that you're using more than one independent variable, okay? You use this when you have two or more independent variable, and it's going to vary depending on what your hypothesis is, of course, as to what those variables are. We use this sort of model when we are dealing with almost anything in political science because we live in a complex social world. Usually, you're not going to be able to explain or predict everything in your dependent variable with just one variable. But for simplicity's sake, within our class, we've only been focusing on bivariate studies and bivariate analysis. But when you read these papers, you see that they have so many variables that they're using to explain the relationship that they see in things. And the reason is because we understand that we live in a complex social world where things are so interrelated and intertwined with each other that we have to include multiple variables in order to have a clear explanation and to get a good R square value, right? But this means that we use multiple independent variables to explain the variation that we see in the dependent variables. So instead of just using education to explain the variation we see in income, we use education, family background, personal motivation, all of these different things. And that's something that's very commonly used in political science analysis. So let's talk about how to interpret this multivariate linear regression. So when it comes to the interpretations for multivariate linear regression, because we've included multiple variables, we have to account for all of those variables. Including those multiple variables is controlling for those variables. And all it means to control for variables is that you are taking these variables' impact into consideration. You're not going to leave out variables and take their impact and apply it to another variable. So taking, for instance, this chart that we have here, this is for a study where we're examining the amount of political comments a person makes and making predictions about that relationship between like their different characteristics and the amount of political comments that they make. So we include all of these variables because we know or we've read the literature and we understand that there are a number of factors that impact the amount of political comments an individual makes. So it might be gender, education, income, race, age, all of these different things that would impact the amount of political comments an individual makes. So in order to be able to understand the relationship properly, we can't just put in one variable that we're interested in. We include multiple, and that's how we get to multiple regression. So if you see a table like this, and it's very common within most journal articles and papers, there's a specific way that you have to interpret them. You have to make sure that when you're interpreting them, you are taking into consideration that you're holding all of these other variables constant, or you're taking them into consideration. That's basically what you're saying there, but it's specific language that you use to describe it. So let's say with female, because there are only two categories for this study, you can only be female or male. Your interpretation of what this means, this negative coefficient here, it means that holding all of these other variables constant, women on average make 1.11 less comments than men about political parties and candidates. So we move on to a variable that's less clear, something like education, because there's more than two categories, but let's say it's in years of education here. How will we interpret this? Well, when it comes to education, holding all of these other variables constant, a 1 year increase in education leads to a 1.22 increase in the number of political comments that we would see. So as a person becomes more educated, we expect to see per year, by each year of education, 1.22 more comments there. Same thing with income. A 1 unit increase in income, holding all of the other things constant, results in a 0.54 increase in political comments. Same thing with marital status. Married people have 0.54 more political comments than those who are unmarried. Let's look at something like race. So let's say, holding all else constant, Black or African American people on average make 0.52 less political comments than those people who are not Black. So it's just a way of looking at the relationship there, and that's what those tables mean. But we just want to make sure that you have a understanding of how to read the tables, because if you were to actually go through with your studies here, you would probably generate a table that looks something like this, and you would need to interpret those variables. So what about instances where we have something like the female thing? How do we even put that in a regression equation? I mean, female is a word, right? It is a nominal variable. How do we even put race in the equation? That is a word. We don't have any, like, you can't be more Black or more white, or you can't be more female or more male. But what has to happen here is that when you have variables that are categorical, you have to go through and you have to recode them and transform them. So categorical variables, just as a reminder, are variables that are nominal or ordinal, and they lack a numerical meaning, and they don't have a fixed distance between their points. So in order to put them in these models, they need to have two or more groups. So like male and female will qualify for that, and race, of course. And then you have to go through and transform them and code them. And that just means that we have to apply an arbitrary numeric value to it so that we can include it within this statistical model. Okay, it doesn't mean that we are saying that women are less than men, or we're saying that whites are more than other races. It means that we're applying some value that we use as our little indicator for that group as to what each of these things are, because we can't impute words. So we give them a number, and then we remember what that number is so that we're able to interpret it when we get all of the stuff generated back out from the numeric table. So what does this look like in practice? If you had that data matrix we talked about before, that spreadsheet, it means that for every female on a line, you would go in and you would put 1 in the gender category, and for every male in that individual participant, you would put 2 in their category, and you would use that when you generate your regression. That's all that you would do there. So we have to go in and transform that so that we can use it, because regression is a statistical package. It is a statistical method. So you have to transform it and code it into some sort of number system so that you'll be able to use regression analysis there. But your next question may be, but what if you have a dependent variable that isn't a number? What if I want to look at something like political party? Because you told me what to do, like if I have independent variables that aren't numbers. But what about if I want to look at something like political party as my dependent variable? What if I want to predict what party a person belongs to? How would I do that? Well, you wouldn't use bivariate regression and you wouldn't use a multivariate regression, but there are models that you can use, regression models that you can use in order to predict something that's categorical. And let's talk about those. When you're dealing with something that has a categorical value, such as like nominal or ordinal, or it could just be one that is dichotomous, where it's just two values of like yes or no, you use a different model called maximum likelihood models. And maximum likelihood models, they simply go through and predict the likelihood of having on a specific outcome on the dependent variable. Now, this doesn't mean that we are predicting something that is would not be suited for that to be the dependent variable, like race. You can't predict somebody's race because that's something that's immovable. That will not be a dependent variable. It's not going to, your income level is not going to be a predictor of your race. That wouldn't work there. But let's say you want to predict like their level of liberalism. That's something that you may be able to do with maximum likelihood because it works for dichotomous dependent variables, and it relies on likelihood models to predict the likelihood of observing one or two possibilities. So like liberal or conservative, right? You want to be able to predict whether or not there is whether this person is liberal or whether or not this person is conservative based on all these other things. And those other things as your independent variables could be something like education level, it could be income, it could be religious affiliation, all that type of stuff, anything along those lines. It could also be things that don't fall into that category. Let's say something like the region somebody lives in, all of that stuff. But when you use a maximum likelihood model, you're trying to predict something that is dichotomous in nature and not really a number, but something that you have transformed in order to get a value for that. Um, the maximum likelihood model, it chooses the value for parameters for which the probability of outcome is the highest. So if you know that, and we're using liberalism and conservatism, you know that the country is more liberal leaning now, then you use this model to predict the likelihood of a person being liberal based upon all of these different independent factors that you include within your model there. So that's how that would work. You could also use a model like this to predict something like a person's vote in an election. You could use the, let's say, a vote for 2016, a vote for Clinton or Trump. And then you could impute all of these different things about them, the region they live in, their educational background, their income levels, their religious affiliation, all of these different things. And then you predict their likelihood of voting for Hillary Clinton or Donald Trump. And that's how a lot of this stuff is used in political science, to model these things and make predictions to better understand political phenomena and the larger political world. So, as I've said, the logic of maximum likelihood is describing the probability of observing a specific outcome, such as in an election, that's something that we commonly see, like with Clinton and with Trump there. We do this by predicting the likelihood of the highest of the outcome that has the highest likelihood of happening. So for the election, we would be talking about Hillary as opposed to Trump, because during that time, Hillary was supposed to have the highest probability of winning. So we would go through and we would have modeled that relationship with all those different factors for all those different individuals, like region, income, past voting preferences, and then we would use all of that information to model the likelihood of a person or this specific person meeting this criteria voting for Clinton as opposed to voting for Trump. Now, one of the most common methods that we use within the within the maximum likelihood models is logistic regression. And logistic regression, what you're trying to do here is to be able to interpret one particular kind of maximum likelihood. The short version of saying this is MLE, using a dichotomous dependent variable. So it's called logit for short, but logistic regression is the long term of saying logit regression. And it's just saying the likelihood of something happening. So an example of this would be the likelihood of somebody deciding to go to college, because that's a dichotomous dependent variable. Go to college, yes or no. So anything that falls into the category of being a dichotomous variable is something that can be used as a dependent variable with a logistic regression model. And there are specific ways in which you have to interpret logistic regression, because it looks different from the linear models, because we're not dealing with like raw numbers like we did with the political comments example. So political comments example, we're just looking at the number of comments a person will make, which would be a raw number, and also a ratio number, because there is an absolute zero that has a meaning, because it means that they're making no comments. But the logistic regression model, you don't have that type of outcome to be able to explain. So the way that you interpret it is a little bit different. You would interpret it as more likely or less likely to do something instead of the amount of comments there, because there's a difference with that. The next thing to consider when using a logistic regression is that you have statistical significance, but you calculate that statistical significance using the standard error and generating a t-value. That's the same way you do when you have bivariate and multivariate regression as well. It's calculated that way. But being able to interpret the magnitude of those coefficients is a little bit different, because you don't have that strict scale number for those coefficients. So again, you're working with more or less likely, as opposed to saying 1.2 more comments than the person who is not, right? Instead, you're saying they're more or likely to do something or to be something, as opposed to being able to put a strict value on how much of something they would do, if that makes sense. But that's how that interpretation works there. This is the more complicated side of research methods that I didn't want to jump too deeply into, especially not earlier in the semester, because it's not really applicable for this class and for the way that I've structured this class. But I would be doing you a disservice if I did not explain some of this stuff to you, or at least attempt to explain some of this stuff to you, because you never know, you might see it, and it will give you a better understanding of the tables and the jargon that you see in the papers that you read. But we're going to stop here, because this is pretty much as we need to cover within this course, and we're going to wrap up everything in our next discussion.